we will be having the first of a series of lectures on raster graphics. In raster graphics, we will essentially be talking of display on raster refresh displays. In the last lecture, I had briefly described what are raster refresh displays or raster refresh terminals or raster refresh type of CRTs. Now, the first display method that we will be talking of is called the DDA, or it stands for digital display digital differential analyzer. The basic idea in this method of drawing lines is that if you have to draw a line from a point x1 y1 to a point x2 y2, we can easily compute the slope of this line, which is delta y by delta x. Therefore, if we know that a particular pixel, okay, this particular pixel is a pixel xy, if this pixel has already been displayed, then the next pixel to be displayed should be a pixel given by x plus delta x and y plus delta y. Okay, or some amount proportional to delta x. So, what we will normally say, it should be epsilon times delta x and epsilon times delta y. Okay, so if we start from the first pixel here, that pixel is, let us say, the pixel xy, then we will display the next pixel, which will be given by x plus epsilon times delta x and y plus epsilon times delta y. As long as we keep incrementing in proportion to the we keep incrementing x and y by amounts proportional to delta x and delta y, we will always get a line which will be in this direction. So, that is the basic idea in this. But the problem that comes is, let us say this is one pixel. Let me just make a small grid. The first pixel that has been displayed is this one. So, this is my xy. Now, I increment x and y, x will become epsilon times delta x plus x and y will become epsilon times delta y plus y. If I take my epsilon to be very small, then this amount will still be the same as x, because x and y are bound to be integers. So, let us say x is, let us say, 100 and y is, let us say, 50, and I take epsilon times delta x to be very small, let us say 0.001, and I take epsilon times delta y to be, let us say, 0.002. Even though I will increment x and y by these amounts, I will still be displaying the same pixel, okay, because 100 plus 0.001 will mean that x will get rounded off to 100 again. So, I will end up displaying the same pixel again. So, I will keep on displaying the same pixel till I am able to increment x by 1 or y by 1. So, this amount epsilon times delta x and epsilon times delta y, these amounts have to be chosen very carefully. If they are very small, then we will end up displaying the same pixel and again and we will be doing wasteful computation. The algorithm will become unnecessarily slow. If I take epsilon delta x or epsilon delta y to be very big, then maybe my line will not be continuous. If I take epsilon delta x to be 1 and epsilon delta y to be 2, I am displaying this pixel, the next pixel to be displayed will be this one. Similarly, the next one to be displayed would be this pixel. Okay, this line will not look continuous. So, the important question is, how do we choose the value of epsilon delta x and epsilon delta y? The choice of epsilon will govern the quality of the algorithm, whether we are able to draw good lines or not. That depends purely on the choice of epsilon. Okay. So, we have two algorithms. One is called the simple DDA. Again, DDA stands for digital differential analyzer, and the other is called the symmetric DDA. The only difference between these two algorithms is the choice of epsilon. Okay. We will just go through both the algorithms and see how they will compare and what kind of results they come up with. Okay. We will start with the symmetric DDA. And we will write this algorithm for drawing a line from a point x1 y1 to a point x2 y2. The first step would be to compute this delta x and delta y. Okay. So, let us say we will call this delta x as x increment, and that will be equal to x2 minus x1. We will say y increment will be equal to y2 minus y1. Okay. Then the way we will compute this epsilon delta x and epsilon delta y would be that, let us say if I take this x increment and y increment and I keep dividing them by 2. Okay, let us say x increment is initially 50, y increment is 100. I keep dividing them by 2. Okay, 50 will become 25, 100 will become 50, this will become 12.5, this will become 25, this will become 6.25, this will become 12.5, then 3.125, 6.25, this will become 1.5625, and this will 3.15, and this will finally become 0.78 something, and this will become 1.5625. Okay. We will keep dividing both of them by 2 till one of them becomes less than 1. Okay, the idea is if you saw what was happening here, if this value of epsilon times delta x becomes very small, then we are doing wasteful computation. If it is very large, we are not displaying the pixels correctly. So, this value epsilon delta x or epsilon delta y, at least one of them has to be less than 1. If both of them are greater than 1, we will end up missing some pixels. So, at least one of them should be less than 1. At the same time, it should not be very much less than 1. If it is very much less than 1, then again we will be doing a lot of wasteful computation. Okay, because if any of them is less than half, let us say, then the same pixel will be displayed again and again. Okay. So, therefore, what we do is we will take x increment, y increment, keep dividing both of them by 2 till at least one at least one of them is less than 1. Okay. So, we will write a piece of code for that. while you are all familiar with the Pascal, I presume. Okay, so I am writing it in a somewhat Pascal like syntax. Okay. So, essentially what we are doing is, in this while loop, while either absolute value of x increment or absolute value of y increment is greater than 1. Okay, if any of them are greater than 1, we will divide both of them by 2. Okay, we will keep repeating this process till both of them become less than or equal to 1. I think I said it wrong earlier. Again? Either of them?
Because this is the
Both of them. Operator has to be and.
While either of them is greater than 1, I will keep dividing. Okay. So, till both of them become less than 1, I will keep dividing. At this point, x increment is 0.78 and y increment is 1.5625. This condition is still satisfied. Absolute value of x increment is greater than 1 or absolute value of y increment is greater than 1. So, I will again carry out this loop, which means this will become 0.39 and this will become 0.78. Okay. So, I will keep dividing till both of them become less than 1. I think I said it wrong earlier. Okay, till both of them become less than 1. Okay. And the first time I find that both of them are less than 1, I will come out of this while loop. Is that alright? So, at the end of this loop, at the end of this while loop, my x increment and y increment, both these variables will have values less than or equal to 1. Okay. In fact, not equal to 1. So, I have put an equal to here, so both of them will be less than 1. And in terms of what I had written earlier, epsilon delta x and epsilon delta y, my x increment is nothing but epsilon times delta x, and the variable y increment is nothing but epsilon times delta y. Okay. Now, in this, both x increment and y increment have to be declared as real numbers. Okay, they cannot be integers. If they are integers, then when I am dividing, when I divide 25 by 2, it will not be 12.5. Okay, it will get truncated and maybe it will be 12. Okay, because of that there will be an error and the slope of the line will not be correct. So, both x increment excuse me and y increment have to be declared as real numbers. Okay. Now, after this stage, we have the values of x increment and y increment. Now, we can start the display part of it. So, what we will do is, we will say x will be initialized to x1. What we are doing now is, this is a screen This is the starting point, this is the end point. The starting point is x1 y1, the ending point is x2 y2. So the variables x y would be the variables of the current displayed pixel, or the variables corresponding to the current displayed pixel. So the first pixel will display will be the pixel x1 y1. The second pixel will display will be x1 y1 incremented by x increment and y increment. So which will be some increment in this direction, and so on. So we will initialize x to be equal to x1 and y to be equal to y1. Okay. Now I said x equal to x1, but I will come back to it for for certain reasons. We will actually be putting it equal to plus 0.5. Okay, both of them. Okay, I will come back to it. Why do we put a plus 0.5? So we write down the full algorithm, then I will explain why we are adding a 0.5 here. Okay, then I have put xy equal to this pixel. I have to keep displaying till I reach my last pixel. Okay, so we say while x is less than x2, do begin. Okay. While x is less than x2, we are doing this. These three statements are being repeated in a loop. The first is plot truncate of x and truncate of y. Let us say I have to draw a line from a point 150 to a point 200, 100. Okay. So initially my x increment is equal to 100 and y increment is equal to 50. I will keep dividing by 2. Okay, so finally I will get this to be probably 0.39 and this would come out to be 0.78. Okay, I am initializing x to be x1 plus 0.5. For the timing, let us take it to be x1. So my x is 100 and y is 50. First time I will plot x y, so pixel number 100 comma 50 will get displayed. Okay. Second time x will get incremented by 0.78, so it will become 100 plus 0.78, which is equal to 100.78, and y will become 50.39. Okay, but now this screen is an array of pixels. In an array I can only address integer locations. So instead of 100.78 I have to address pixel number 101. I will round it off, and instead of 50.39 I will address pixel number 50. So the pixel to be displayed after the pixel number 100 comma 50 will be the pixel 101 comma 50. Is that understood? Okay. If the pixel to be displayed is 101 comma 50, that is, if this is 150, 101 comma 50 will be this pixel. Now instead of rounding off, if you notice I put truncation over here. Okay, if I am truncating, 100.78 will actually become 100. Okay, but instead of x1 I have put x1 plus 0.5. Okay, so initially my pixel 150, so xy became 100.5 and y became 50.5. In the first cycle, I truncated both these numbers and displayed 100 and 50. Okay, displayed the pixel numbered as 100, 50. In the second time when I come here, my x will be 100. Okay, I'll write it here again. X will be 100.5 plus 0.78 and y will be 50.5 plus 0.78. Sorry, 0.39.
So would it be same if we use the command round off without initializing the value of x and y by increasing 0.5?
That's right. If we do not put this 0.5 here, then we will replace truncation by rounding off.
The same thing. No?
It will be the same thing. Okay, but since we are putting 0.5 here, we are putting truncation instead of rounding off. Okay, that is exactly what I was trying to come to. This now x will become 101.28 and this will become 50.89. Now when I truncate these two, I will still get 101, 50, which is this. Okay. Now the result of adding 0.5 here and then truncating is the same as if I don't add 0.5 here and do a rounding off. Is that appreciated? Okay. In general, if you take any number x, okay, round of x would be the same as truncation of x plus 0.5. Okay, this you can check up for any number. Okay, that is why here we are adding 0.5 in the beginning and then truncating every time. And the reason we prefer to do this is truncation is much faster than rounding off. Okay, truncation takes much more time, sorry, the other way around. Rounding off is very slow and truncation is faster. Okay, so we prefer to truncate rather than rounding it out. Okay.
But this is only same for the first two pixels. The rounding off and truncation will means coincide. No. But for the rest afterwards, then there will
For
be
all of them, it will coincide.
no. For example, you take the third point, that will be different.
No, let's just
Yeah.
let's
Yeah, if you would be adding 0.5 out there, the equation of line will be changing. Like
Yeah.
we can't add inside the loop.
just say. In one case, we will start with 150. We are starting with 150. This will become 100.78, 50.39. Then the next time it will become, add 0.78 again, 101.56. This will become 50.78. Then it will become, we will add 0.78 again, so this will become 102.34, is that right? And this will become 51.17, okay, and so on. In this case, we are supposed to round off. So this one becomes 101, this will become 50, this will be 102, this will be 51. This will still be 102 and this will be 51. Is that okay? Now, I have added 0.5 in the beginning itself. So this becomes 100.5 and 50.5. This will be 101.28 and 50.89. This one will be 102.06 and this will be 51.28. This will be 102.84 and this will be 51.67. Okay. Now when I truncate, this will become 101, this will become 50, this will become 102 This will be 51. This will become 102 and this will be 51. The results are the same. See, basically when I have added 0.5 in the beginning, that 0.5 is carried over in all the iterations. All these numbers will be 0.5 higher than these numbers. Okay, I have added 0.5 only in the beginning, but that effect will remain in all the iterations, in all the cycles, let us say. So, initially this number is 0.5 higher than this is also 0.5 higher than this is also 0.5 higher than this. Okay, so this effect will go on in all the iterations. As a result, if I take any of these numbers, the result of truncating them will be the same as what I will get from here. Is that okay? So, coming back to this algorithm, so what we have done is we have started with the pixel xy and we have displayed pixels in the direction of the slope by adding x increment and y increment every time. Okay, and instead of rounding it off, we have added 0.5 in the beginning and then we are truncating it every time. Okay, and how we have found out x increment and y increment? We took delta x, that is x2 minus x1, and delta y, which is y2 minus y1, and kept on dividing them by 2 till both of them were less than 1. Okay, so this is referred to as a symmetric DDA algorithm, a symmetric digital differential analyzer. Okay, any question on this symmetric DDA algorithm? Okay. Now we will see the algorithm which is referred to as a simple DDA. If we have to draw a line from this point to this point, in the symmetric DDA, what we did was we took increments in x direction and y direction depending on the multiples of 2. Okay, that means we have taken delta x and delta y. Essentially what we did was we took the higher of the two. Let us say if the higher of the two is 50, we found out some number 2 to the power n which is bigger than 50. Okay, some multiple of 2 which is bigger than 50, and we divided both of them by that. Okay, so because we were dividing both delta x and delta y by 2 every time. Okay, so if you are taking 50, so 2 to the power 6, 4, 16, yeah, 2 to the power 6 is equal to 64. Okay, so we are dividing this by 64, and delta x, let us say if it is 25, we are dividing that also by 64. So this delta x and this delta y are both being divided by 2 to the power n. In a simple DDA, instead of dividing it by 2 to the power n, we will divide it by higher of delta x or delta y. Okay, so that out of delta x and delta y, at least one of them should be equal to 1. Between delta x and delta y, if let us say one is 25, the other is 50, we will divide both of them by 50. Not clear? My total increment in the x direction, let us say, is 25. My total increment in the y direction, let us say, is 50. Instead of dividing it by 64, now we will divide it by 50. So that the increment that I will take in the x direction will be 25 by 50 or 0.5, and the increment that I will take in the y direction will be 50 by 50 or 1.0. As a result, either delta x or delta y will always be equal to 1. One of the two will always be 1. In the symmetric DDA case, both of them were necessarily less than 1. In this case, one of them has to be equal to 1. Okay. The basic the reason behind doing this is that if my increment in both the directions is less than 1, then it is possible that I will end up displaying the same pixel again. Okay. While if one of them at least is equal to 1, then that will not happen, because in one direction at least I am incrementing by a amount equal to 1. Okay. Of course, in the symmetric DDA also we will never end up displaying the same pixel again. That will not happen in the symmetric DDA either. Somebody said something?
That was happening.
Again?
That was happening. That was happening in the last example.
The last 3 points that you are taking,
Yeah.
last 2 were same.
Okay. Okay. So these 2 points were being the same. You are right. In the symmetric DDA, these 2 points can be the same because the increment was less than 1. But if my increment is more than 1, at least one of the 2 increments is equal to 1, then the same point will never get displayed again, because at least one of the pixels will shift. The next pixel to be displayed either in the x direction or in the y direction, it will be incremented by 1. Okay. So in this case, if my delta y is equal to 1, in that case every time I will take a pixel in a new row. So every time I am increasing delta y by 1. Delta x may or may not increase, okay, but delta y will definitely increase. Okay, that is in the simple DDA. So we will just write down the algorithm for this and see how it compares. If you look at a symmetric DDA, this is the algorithm we had written. Now in contrast to this, we will retain these 2 steps and this part will now change. Okay, in fact these will also not be required. What we will do is simple DDA. We will take a variable, let us say length, which will be, to start with, let us say absolute value of x2 minus x1. Okay. Then we will say if absolute value of y2 minus y1 is greater than length, then length will be equal to absolute value of y2 minus y1. Okay, essentially between x2 minus x1 and y2 minus y1, whichever is greater in magnitude, that we are assigning equal to length. Okay, and then we will say x increment will be equal to x2 minus x1 divided by length, and y increment will be equal to y2 minus y1 divided by length. Is that okay? Once we have calculated x increment and y increment, then the rest of the algorithm will remain the same. Okay, basically this loop for displaying the line is still the same. We have already found out what is the value of x increment and y increment. We know the starting point. We will repeat it in the same loop. and we will be able to draw the complete line. Okay. The difference between these two algorithms the first difference is essentially the value of epsilon delta x. Okay, in symmetric DDA, both epsilon delta x and epsilon delta y are less than 1. In the simple DDA, either epsilon delta x or epsilon delta y will be equal to 1. Okay, one of them will always be equal to 1. Okay, this is in the case of simple. Okay, as a result, in the simple DDA, there will be no repetition of points. Or repetition of pixels. The same pixel will not be displayed again. Okay. In fact, I'll just show you some lines drawn by the two algorithms. Are you able to see it? This figure. Can you see it clearly? This is the line drawing by a symmetrical DDA. Okay. In contrast to this, a line drawn by the simple DDA would look something like this. Is it visible? I hope so. Okay. If you notice the difference between the two, yes, the number of points in simple are less. Okay, just the blue circle that I have made, those are the lines or the pixels selected under the symmetric DDA. And the black crosses are the ones selected under the simple DDA. These pixels are extra in the case of symmetric DDA. Okay, so the symmetric DDA draws more pixels than the simple DDA. Okay, so the simple DDA always draws less number of pixels. Okay, and the reason is, let us say if delta x is less than delta y, that means the line is travelling more in the y direction. If the line is travelling more in the y direction, then in the y direction you are at least incrementing by 1 pixel every time. Okay. So, in the y direction you will always be moving by 1 pixel. Okay, so in every iteration you are going to a different row of pixels. Well, that need not be the case in symmetric DDA. In the y direction also your increment will be less than 1. Okay, so on the same line you will end up drawing sometimes 2 pixels before going on to the next line. Okay, and that is what is happening in this case. Here in the x direction the slope is more, the movement is more in the x direction. Okay, so in the simple DDA, every time you move in the x direction, you'll every time you draw a new pixel, you'll at least move in the x direction by 1. Okay, so that is why you can see in the black crosses, and you go from one pixel to a second pixel, they are always moving in the x direction at least by 1 pixel. Well, that is not true in the case of the symmetric DDA. This is 1 pixel drawn, the next pixel drawn is here. So in the x direction you have not moved at all. Okay, similarly here 1 pixel was drawn, the next pixel drawn is this one.
Then why this choice of 2 to the power of 64 or 2 powers of 2? Why don't we have just 1.5 times the length?
Okay, that's a good question. Okay, essentially what he has asked is, let's say delta x is 25 and delta y is 50. We kept on dividing by 2 in every iteration till both the numbers became less than 1. Why divide it by 2? Anyone trying to make a guess on that? Why should you divide by 2 every time?
What I am saying is that instead of why divide 2, like 2 is obvious because left shifting it will give a faster computation.
Okay.
But using the same algorithm, at the end when we found the length, we just multiply the length by 1.5 and say that divide by that. That will be a faster algorithm than even this because this is in a loop, that one won't be in a loop.
Okay, I'll explain both the points. See, the first reason, the first part of the question is why we are dividing by 2 every time. Okay, and the reason he has given himself, that is division by 2 is simpler than division by any other number. Okay, when you are trying to divide any number by 2, let's say your number is, you want to divide it by 2, all that you have to do is a right shift. Okay, if you want to multiply it by 2, all that you do is a left shift. Okay, that means if you want to divide this by 2, let's say this is your number, this will just become something like this. This is this number divided by 2. If you want to multiply this number by 2, all that you will do is a left shift and this number will become like this. Okay, so division by 2 is much easier to implement than division by any other number. Therefore, we choose a multiple of 2 and we keep dividing by 2 every time. Okay. The second thing he is saying is that why divide by 2 at all? In the simple DDA, we found out the value of length, right, at this stage. All that we need to do is just say length is equal to length multiplied by 1.5 or some such number. If you notice, this value of length will give you a different set of pixels than what the symmetric DDA gives. It will not give the same set of pixels, because when you are multiplying by 2 to the power n, this figure 2 to the power 6 equal to 64 is not equal to 1.5 times length.
No, but why do we care? Why do we care? Why should we have a line which is the same as a symmetric algorithm?
There is no reason for you to have the same line as such. Okay, but what I am saying is that yes, you can do something like this. You will get a different set of pixels. Okay, whether this is more efficient than the symmetric DDA, that I won't say, for the simple reason that we are having what is called divisions over here. Okay, we are having 2 divisions. Divisions are more expensive than dividing by 2. Okay, so this algorithm is likely to be less efficient than the symmetric DDA. The advantage that symmetric DDA has over simple DDA is its speed, because there is no division involved and we are only doing a right shift, a left shift. Okay, so the advantage of the simple DDA is the speed. If you use this modified algorithm, then we lose that advantage. Yes, this algorithm will also work. you will get a set of pixels which will be able to display that line. Okay, but the disadvantage compared to the symmetric DDA would be the loss in speed. Okay. So we are just comparing the two algorithms. We said in simple DDA there is no repetition of pixels, but simple DDA has divisions. Okay, divisions make the algorithm much slower. We will now see another algorithm which is called a Bresenim's line drawing algorithm. We will describe the basic principle of this algorithm today, and then we will go into details in the next lecture. I say this is the array of pixels, and you want to draw a line from one point here to some point here. Okay. Now this line is what your line should actually look like. Okay, so we will call this as the true line. Now if we actually select a set of pixels, let us say this is one pixel I select, maybe this is the next pixel I select, this is another pixel, this is one pixel, this is one pixel, and so on. When I am selecting this pixel, actually if I consider center, this is the point that has been selected. Okay, or if I am talking of the starting plane, this is the place, this is the point which has been selected. The distance of this point from this line is this. Okay. When I select the next pixel, let us say this one, the pixel that is being selected is at this location. I am talking of at the start of the pixel. This is the point. So here the distance of this location from this true line is this much. Okay. So the set of pixels that are actually displayed, these constitute what we call as the displayed line. Okay. This straight line that I have drawn, that is a true line. Now the Bresenim's line drawing algorithm works on the principle that the distance between these two lines should be the minimum. Okay, this distance E, that is actually the error that is there between the displayed line and the true line. Okay, so this E is the error. Okay, or we will say gap between true line and displayed line. Okay, and the Bresenim's line drawing algorithm works on the principle of minimizing this error. Again, please.
Root mean square distance or simple distance? Like sum of root mean square distance minimizing.
We will come to that. Whether we consider the root mean square distance, perpendicular distance, or the distance along the x-axis or the distance along y-axis, we will come to that soon. Essentially what we do is, just to give a brief idea, we take the direction of maximum movement and we measure the error in a direction perpendicular to that. Okay, we will come to that later on. Okay, but the basic idea is that we try to minimize this error. In the previous algorithm, simple DDA or the symmetric DDA, we were not talking of this error at all. Okay, we are just displaying pixels in the direction of the slope. We had not even defined a error. We are not bothered about whether there is any error between a displayed line and a true line. Okay, so we will see this algorithm in detail in the next class. We will stop here now, and next time we will see this algorithm in more detail.